Section 9.5. Okay, let's start up here again with section 9.5. We've talked about how to name an alkyne, how to make an alkyne, and we talked about where you would find an alkane in nature, or an alkyne in nature. Now we're going to talk about reactions that you can do with an alkyne, and we're starting off with reduction, namely catalytic hydrogenation. So just like we saw the hydrogenation of an alkene in chapter 8, you can do the same type of catalytic hydrogenation with an alkyne, where if you take an alkyne like 2-butyne and you treat that with hydrogen, palladium, and this, or platinum or nickel, so we'll put here palladium or nickel as well, that will reduce the triple bond completely, and you go from an alkyne to an alkane. So you go from 2-butyne to butane. It says here that the first addition produces a cis alkene, right? And that makes sense because we looked at the mechanism of hydrogenation in chapter 8, and we said it occurs with syn addition because the pi bond is approaching the surface of the catalyst. So it makes sense that you'd proceed through a cis alkene. However, it doesn't stop there, and you can't isolate the cis alkene. It just keeps going until you get to the fully hydrogenated product. So that's catalytic hydrogenation. Now you might be asking, well, is there a way that I could stop here at the alkene? Could that be done? And the answer is yes, it can be done. You can stop at the cis alkene if you use what's called a poisoned catalyst. So a poisoned catalyst. And if you're wondering, what is a poisoned catalyst? Well, there are a couple of them. The one that my students like the most is Lindlar's catalyst, because I just asked them to remember the name. Just Lindlar's catalyst, and that suffices to produce a cis alkene. It's a mixture of these compounds, so barium sulfate and quinoline and palladium on barium sulfate and methanol. Don't worry about that. I'm not going to ask you a whole bunch about the Lindlar's catalyst. However, it can reduce the alkyne to a cis alkene. There are other catalysts as well. One is this nickel boron complex, which we call the P2 catalyst sometimes. So you can write P2 as well. I've taught the class long enough to know that students usually don't write P2. They like Lindlar's catalyst. But if you write it down in a quiz, I would certainly know what you're talking about. So that works as well. Anyhow, so that's enough information about Lindlar's catalyst and the P2 catalyst. But the bottom line is that they stop at the cis alkene. Very cool chemistry. Now, if you're wondering, well, how does that work? Well, what happens is that the poison catalyst lowers the activation energy and changes the pathway for the first reduction only. Only the first reduction. The second step, the second equivalent of hydrogen, is not added across the double bond because that step is not catalyzed by the poisoned catalyst. Again, going back to catalysts, way back to your Gen Chem days, what does the catalyst do? Well, it lowers activation energy. However, this is a two-step process: hydrogenation to make the alkene, and then hydrogenation again to make the alkane. But the poison catalyst only lowers the activation energy for the first hydrogenation. And there you have it. That's how a poison catalyst works. Well, that produces a cis alkene. If you're wondering, is there a way to make a trans alkene? Can we do that? The answer is we can. Very different set of conditions. No hydrogen gas involved here. What we do is something called dissolving metal reduction. You literally take sodium, which is a metal. Sodium is the metal that we use, and we dissolve it in liquid ammonia. And when you dissolve sodium in liquid ammonia, you produce a transalkene. And this reaction is stereoselective for the anti-addition of the two hydrogens. They are trans to each other. We don't get the cis alkene in this case. Now, keep in mind that these conditions, sodium and ammonia, are not to be confused with sodium amide, right? NaNH2. Okay, this is a strong base that we use to deprotonate a terminal alkyne. This is used for reduction. So remember that reduction is when something gains electrons. So reduction, and it functions as an electron donor. We know that sodium is in group 1, It has one valence electron to donate. And so that is how we end up producing the transalkene. Well, what do I mean by that? Well, what I mean is this, is that when the alkyne reacts with the sodium in liquid ammonia, you end up donating an electron to the double bond, or sorry, to across the triple bond, and you end up forming an intermediate that's called a radical anion. So check this out. It's called a radical anion. Now, after we donate an electron, there's two possibilities. We can have a radical anion where we have an anion pointing up and the radical pointing down like this. And you can imagine that this would be lower in energy than if you had the radical and the anion on the same side of the double bond because of the electron-electron repulsion. So because the radical anion, when it's trans, so to speak, is lower in energy, this is the rationale as to why we only get the trans product. Now, there is a mechanism shown in the book for this reaction. There is a mechanism shown in there. However, I'm not going to ask you that mechanism. It's mechanism, I'll just write it down here. It's mechanism 9.1. And I'm going to write here, will not ask, but study anyhow. It would be a good idea to look at it. And if you're asking me, well, why would you tell me to study it if you're not going to ask it? Because it will provide the rationale for the formation of the transalkene. But the reason why I'm not going to ask it is because it is a radical mechanism. It involves fishhook arrows, which show the movement of only one electron, and that is covered in more detail in the next chapter. So in that chapter, we'll talk about fishhook arrows in detail. And again, a fishhook arrow is nothing more than an arrow that shows the movement of an unpaired electron, just one electron. You know what I could do, though, is just kind of show you the first step after I said I wasn't going to. Let me just show you the first step quickly, how we form that radical anion. So you start with your alkyne, and in the first step, sodium, remember, if we draw the Lewis structure of sodium, it's just this. Sodium has one valence electron. So what it does is it's going to donate, okay, it's going to donate that electron like this. Maybe I'll draw it like this, okay, to keep it consistent. So it's going to donate this electron. Then you form a pair of electrons, and then you have the radical coming down here like this. Again, I'm not going to ask you to draw this mechanism on your quiz. However, it is a good idea to know how you form the radical anion. Can I just get a thumbs up if everybody follows me on the radical anion? We're talking about a pair of electrons and an unpaired electron. Well, they're not going to want to be near each other, right? They're going to get as far away from each other as possible. Okay, cool. So after another electron is donated and a couple of proton transfers, you end up with a transalkene. You can see that I even put it here in the text. You don't have to memorize it. We're going to go over this in detail in chapter 10. All right. So here is a summary of what we've covered in this section. We talked about how to take an alkyne and to reduce it to an alkene, a cisalkene, using Lindlar's catalyst or a poison catalyst, the P2 catalyst. Then we looked at this in chapter 8, that you can completely reduce an alkene to an alkane. You can also do the same thing. You can reduce an alkyne completely to an alkane. There's no problem with doing that. And then we talked about the reduction of an internal alkyne to a trans alkene. And then, of course, you can fully hydrogenate that. One more aside that I want to mention, I don't think I have it in my slide, so I'm going to put it in here, is this is an internal alkyne. If you have a terminal alkyne, so let me just draw something like this. So I'll put a terminal alkyne. If you want to reduce a terminal alkyne to an alkene, the only way that we have to do that is to use hydrogen and Lindlar's catalyst. Now there's no cis or trans. Okay, you're just going to end up with this compound, okay, where you have the double bond on the end. However, the reason I bring that up is because students think, well, maybe I could do the same thing with sodium and liquid ammonia, and then I'm going to end up with this as well. And the answer is no, that will not work. Okay. The reason why is because the sodium just deprotonates the terminal alkyne to give you an alkanide. So that will not work. If you want to reduce a terminal alkyne to an alkene, you can't use either method. You can only use hydrogenation conditions with a poison catalyst. Cool, and that is actually mentioned in the textbook, so it's something I expect you to be fully aware of. All right, now that we've talked about the reduction of alkynes, let's see if we can try some practice problems here, and I'll show you a little mnemonic that my students devised a few years ago. Okay, first one, we have diisopropyl acetylene. This compound, if we want to make a cis alkene, who could tell me what the conditions would be to make a cis alkene? Not a trick question. We just looked at it. What do you want to do if you want to make a cis alkene? Yes, absolutely. Somebody just wrote the poison catalyst. Yeah. So I would just write hydrogen and Lindlar's catalyst. There we go. Right. Absolutely. My students are all 100% correct. The next one, if we want to make the trans alkene, we're going to have to use sodium metal reduction. So that's called dissolving metal reduction. So we use sodium in liquid ammonia. And the mnemonic that my students devised years ago is that since sodium is used to make a trans alkene, they showed me this. So if you have a trans well, that's not really good. That's kind of ugly. But if you have a trans alkene like this, they said, you know, you put a bond, it kind of looks like sodium, like the letter N. Anyhow, this is something my students came up with. Mr. Dion did not devise this. But if it helps you, it's all good. What else? Next one, we want to make a trans alkene again. Well, we just looked at that. So sodium, dissolving metal reduction. And the last one is just completely reducing the alkyne to an alkane. So for that, we just use hydrogen and palladium, platinum, or nickel. Let's choose palladium just for fun. And there you go. So that's reduction. That summarizes everything you need to know about alkyne reduction for this chapter. We learned how to make a cis alkene, trans alkene. We talked about the little kind of variation, not variation, I guess it's more of a note that when you have a terminal alkyne and you want to reduce that to an alkene, you can't use sodium. You've got to use Lindlar's catalyst. So we got that down. All right, let's move on to the next section. You know, chemistry is a content-driven subject. And let's move on to the next section, which deals with hydrohalogenation of alkynes. Remember that hydrohalogenation is nothing more than the addition of HCl, HBr, or HI, right? A hydrogen and a halogen. We don't talk about HF. That's something a little bit different. But back in chapter 8, we looked at all kinds of hydrohalogenations to alkenes. We talked about Markovnikov addition and how that addition occurs via Markovnikov addition. Well, you see the exact same thing occurs with an alkyne. If we take an alkyne and we treat it with HX, HCl, HBr, or HI, we get the addition of the hydrogen atom and the halogen in a Markovnikov fashion. All right. If you use excess HX, right here, we're assuming that we're only using one equivalent. So if you have 1 mole of this, right, you're using 1 mole of this, that will give you this alkene. However, if you use excess HX, it just keeps going over and over and over, right? And it adds in a Markovnikov fashion. So we get basically like a double Markovnikov addition across that triple bond. Well, that covers hydrohalogenation. We can either do monohydrohalogenation or we can do double hydrohalogenation. You might be wondering, well, Mr. Dion, I remember that we looked at anti-Markovnikov addition across a double bond with HBr and peroxides. Can you do it on an alkyne? And the answer is yes. Okay. Before we get into, oh, I see. You do not need to know the mechanism of these. So basically, I'm not going to ask you the mechanism of this. Yeah, don't worry about that. If there's a mechanism you need to know, I'll tell you. All right. What I was trying to say before I interrupted my own self was if you want to do the anti-Markovnikov addition of HBr across a triple bond, it can be done. It's totally doable. It's anti-Markovnikov is just the same old HBr and peroxides, except you get a mixture of E and Z. Now, again, I'm not going to quiz you on this mechanism because we're going to cover it in detail in chapter 10. If you remember back in chapter 8, when I first brought up peroxides and HBr, I told you that it was a radical mechanism. And again, we cover radical mechanisms in detail in chapter 10. So we'll reveal all the stuff there. Let's try a practice problem. Let's put our thinking caps on here. Oh, I had one more slide I wanted to show you. I thought I had a practice problem. Yeah, it's right here. So this is nothing more than really a kind of a semi-summary of some of the things we've looked at. So you can take an alkyne and you can make a dihalide from it. Well, what did we talk about? Or what did we say dihalides were useful for? Well, we said we can do a double elimination and we can make an alkyne. So now you know how to make the dihalide, and now you know how to make the alkyne from the dihalide. So that doesn't seem very useful, but each reaction in its own right is useful. Okay, so that's just more, kind of putting the things together, connecting the dots, so to speak. Let's take a look at question 9.13. It says, predict the major products expected for each of the following reactions. Okay, let's give it the old college try. We've got this geminal dichloro here. In the first step, we're treating it with excess sodium amide. So we're going to do a double elimination followed by deprotonation. So after step 1, what you would have would be this, your aromatic ring, and then you would have the alkynide like that. After step 2, you're going to add the proton. So after step 2, you end up with, I'll just use pH to abbreviate, you end up putting the proton on the end. And then in the last step, if you have HBr and peroxides, is that going to add HBr in a Markovnikov or an anti-Markovnikov fashion? Could anybody tell me? Anybody? Would this be Markovnikov or anti-Markovnikov? Exactly. The students definitely know that this is anti-Markovnikov, and so what you end up with would be this compound where we have the bromine added here, and that's the trans compound, so that's E. You're also going to end up with some Z compound as well, so we'll draw the Z compound, which is this, like this. So we end up with E and Z, Eposit and Zame, as my students like to call it. All right, there we go. Not too bad. I'm just going to delete those intermediates for the sake of space. Oops, I need to do that. Just bear with me. You guys can take a look at the next one. I'm trying to get this all squared away here. So we got this guy, and we got this guy up here. All right. There we go. All right. The next one, well, the first 2 steps are the exact same as they were before. So we're going to end up, oops, where's my black pen? After the first 2 steps, we're going to end up with this compound. So this would be called phenylacetylene, is what I would call that. And then after the last step, when we have excess HBr, we're going to do a double Markovnikov addition of HBr. And we're going to end up with the geminal dibromide, just like that. All right, here we go. What do you think? Not too bad? Well, you don't have to answer that if you don't want to, but anyhow, I think it's pretty reasonable. A few new reactions. Okay, so what have we covered? If you go all the way to the back, or the bottom, so to speak, of the slides, if you go all the way down here, this is what we're getting at, is learning all of these reactions. Now let's hold the phone before you get, intimidated. We've already looked at a bunch of these reactions. We've looked at the first reaction, which was where we take a geminal or a vicinal dihalide and we make an alkyne, double elimination, followed by deprotonation, then protonation. So we've covered reaction number 1. Son of a gun. We've covered these reactions. Then reaction number 2, we said excess HX gives us the double hydrohalogenation. Then we said if you have one equivalent, then you can just add 1 molecule of HX across your triple bond. What else? We've covered reduction with Lindlar's catalyst to make a cis-alkene. So we've got this reaction down. We covered complete hydrogenation. We covered sodium metal reduction. And so everything that has a red check mark by it, we've done it. Now, I think what we're going to take a look at next are going to be these two reactions. What these are hydration reactions, both Markovnikov and anti-Markovnikov. I'm not going to ask you the mechanism for either of these reactions. I'll talk about them a little bit, but I'm not going to go into detail about them. However, I do expect you to know the mechanism of something called tautomerization. So now that you've heard that word, that is a mechanism I expect you to know. It's a pretty quick mechanism, but that's an important one. So let's go back into the slides and find out where we were. We were here, we did that problem, took a look at this, we solved that problem, and that brings us to hydration of alkynes. Hydration is nothing more than the addition of water across our triple bond. And if you remember back in chapter 8, with alkenes, we talked about Markovnikov addition of water across a double bond. We talked about we talked about oxymercuration, demercuration, which is a way to add water in a Markovnikov fashion and to avoid carbocation rearrangements. Went over that in detail. And then we talked about hydroboration oxidation, which was a way to do anti-Markovnikov addition of water across a triple bond. Well, based off of all that knowledge, you might think, okay, well, if I just take an alkyne and I just treat it with some aqueous acid, so just some H3O plus, I'm going to add water in a Markovnikov fashion. Let's just imagine, and you don't have to write this down because it's not going to work. But if you did this, you might think, thing. So what we do is we spruce up the reaction conditions. We still mix water with a strong acid, sulfuric acid, but we use this compound, which is mercuric sulfate, or mercury 2 sulfate, either way. We use mercuric sulfate to spruce up the reaction conditions and make the alkyne more reactive, because this is not going to happen. Then, after you've added the water in a Markovnikov fashion, you end up getting something called an enol, and I'm going to talk about that in a little bit. And the enol undergoes a process called Tautomerization, which produces a ketone. Okay, so the bottom line is, if you have a terminal alkyne, so this slide can be summarized like this: terminal alkyne, treat it with sulfuric acid, water, mercury 2 sulfate, HgSO4, and you end up with a methyl ketone. Right? The reason we call this a methyl ketone is because you have a CH3 here, methyl ketone. All right, well, let's dig in a little deeper here and talk about that tautomerization. Because after you add the water in a Markovnikov fashion, you end up with this kind of functionality here, and this is called an enol. You can imagine that this comes from en for the alkene, and then ol for the alcohol, an enol. But an enol undergoes a rearrangement, so to speak, or an isomerization, I guess is the better word for it. It undergoes an isomerization that we call a tautomerization. Now pay close attention to me here, okay? The definition of tautomerization is an isomerization that involves the movement of a pi bond and a proton. So a pi bond and a hydrogen atom. And you can see that as we go from the enol here on the far left to the ketone, what moved is this proton is now over here, and the double bond went from here to over here. So that's tautomerization. Now, how does this happen? It's just two proton transfers. Since we do the reaction in acid, the first step is to protonate the double bond to make this carbocation, which is resonance stabilized. Then you form this oxonium, which undergoes a second proton transfer to give you the ketone. Know this mechanism. This comes up a lot in organic chemistry. The ACS, the MCAT, they love to ask this mechanism. It's a very quick one, but it's a very important one for organic chemists. So we say that the ketone and the enol, we say that they are tautomers of each other, right? They interconvert via an isomerization process that is called tautomerization. And the equilibrium, generally speaking, favors the ketone. So if you have an equilibrium between the enol, this is the enol, and the ketone, the equilibrium is generally speaking going to favor the ketone. There are exceptions to this rule, but we're not worried about them today. That's not really what the focus of the chapter is. So there you go, keto-enol tautomerization. Now, if you do the acid catalyzed hydration of an unsymmetrical internal alkyne, well, that will give you two ketones, because there's both of these carbons, neither of them have a hydrogen on them. So there's no Markovnikov and anti-Markovnikov. You're going to get a mixture where you end up with the carbonyl on the blue carbon, and then you're going to end up with half of it being a ketone where the carbonyl is on the red carbon. And so it's not all that useful to do the hydration of an internal alkyne unless it's symmetrical. If it's symmetrical, then you end up with ketones that are identical and it's all good. But if it's unsymmetrical, it's kind of, I wouldn't say useless, but it's not the greatest reaction out there. All right. So somebody asked me to repeat the definition of tautomerization. So if you go to the textbook, there is a definition of tautomerization. Tautomerization is an isomerization process that involves the movement of a hydrogen atom and a proton. Okay, hydrogen atom and a proton. All right, well, let's take a look at a question here. Question 9.18, it says, draw the major products that you expect when each of these alkynes, well, there's only one, is treated with aqueous acid in the presence of mercuric sulfate. So we've got sulfuric acid in water, and we've got some HgSO4. What do we get? Well, we get a Markovnikov addition. Remember, you need this mercuric sulfate in order to get the reaction to go. If you just put acid in water, it doesn't work. The details are found in the textbook. The textbook does give a little bit of information about the mechanism. However, if it's not in my slides and I didn't tell you, you need to know it, I'm not going to ask you about that mechanism. I would think it's a good idea to take a look at it because it will provide you with a rationale. However, I will not come out and ask you that mechanism. It's not in my slides. I didn't go over it with you in class. Don't worry about it. If there's a mechanism you need to know, like the ones today, I told you which ones. Okay, so if we look at these two carbons, the carbon that I'm highlighting in red has no hydrogens attached to it. The carbon in blue has one hydrogen attached to it. This is Markovnikov addition. Markovnikov. The rich get richer. So the carbon that's in blue is going to take the hydrogen. The carbon in red is going to take the hydroxyl. Let's draw what that looks like. You go from sp hybridized carbons to sp2 hybridized carbons. Now you've got a second proton out here, and you've got the hydroxyl here. This is an enol. Enol. You do not isolate the enol. It is not stable. It undergoes tautomerization. So tautomerization. So I'll put tautomerization. Okay, like that. And we end up moving the pi bond from between the two carbons to between the carbon and the oxygen. And we take this proton and we put it on this carbon. Oh, what do we get? We get something that looks like this. We get a methyl ketone, just like I told you before. Now, this tautomerization process, the way that we describe the relationship between the enol and the ketone form, so this is the ketone, obviously. Okay, we say that these two, we say that they are tautomers of each other, tautomers. Okay, we don't call them, They are isomers. They're constitutional isomers, but the proper name that we would use would be they are tautomers of each other, the ketone and the enol. And make sure you can draw the mechanism of the keto-enol tautomerization. Okay, with all that in mind, let's try another one, hydration of alkynes. Now we have what? It says, identify the alkyne you would use to prepare each of the following ketones. So now we're trying to come up with the starting material that we'd want to use to make this, right? To make this ketone. And if we have a methyl ketone, which this is a methyl ketone. If we think in terms of retrosynthesis, the enol would be this, where the double bond would be here. Okay, like that. That would be the enol form. So this is the enol form. And where is that going to come from? That is going to come from this compound, where we have the triple bond right here, like that. So this is the starting material that we would need for our reaction. This is what? 1, 2, 3, 4, 5. So this would be 4-methyl 1-pentyne. And what we would do is we would take this and we would just treat it with sulfuric acid, water, and some mercuric sulfate, and that's going to give us the desired product. That one's kind of straightforward-ish, I would say. This one is a little more complex because now you have not a methyl ketone, you have an ethyl group on this side and a propyl group on this side. So let's see, we could either think about making this compound from this enol. So let me draw, we could have the enol where the double bond is on this side. Okay, like that. Or, and I'm just going to write this in green, you could think about making this, if you had the double bond on this side, that would also undergo tautomerization to give you the ketone. However, the problem with the one in green is that if you start out with this alkyne, so where we have the double bond or the triple bond here, then you have 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. The problem with this is that you'd end up with the carbonyl on this carbon, and then you'd also end up with the carbonyl on this carbon. You'd end up with a mixture because this is an unsymmetrical alkyne. However, if you use the red enol, okay, and you do a retrosynthesis on that, well, then you'd have a symmetrical ketone. So 1, 2, 3, 1, 2, 3. And since this is, did I say a symmetrical ketone? I meant a symmetrical alkyne. Since this is symmetrical, this is the one we're going to want to use. This is unsymmetrical. And if you remember back here, I said that if you have an unsymmetrical internal alkyne, it gives you a mixture. Whereas if you have a symmetrical internal alkyne, it's only going to give you one product. It wouldn't matter. So let me just delete the carbons on here, okay? It wouldn't matter if the ketone was on here or on here. You're still going to end up with the carbonyl in the right place. All right? Give me a thumbs up if you follow me on that one, the rationale for the symmetrical versus the unsymmetrical. Okay, cool. Yeah, great. There we go. So let's continue on with hydration. Before we take a break, I want to show you another reaction that involves hydration. So now we've covered Markovnikov hydration. The conditions are shown right here. Sulfuric acid, water, and mercuric sulfate. Now we're going to talk about anti-Markovnikov addition. How do you add water in an anti-Markovnikov fashion to a triple bond? We use the same conditions or similar conditions to what we did with alkenes. We use hydroboration oxidation. Who remembers this chestnut, right? Borane and THF, followed by hydrogen peroxide and sodium hydroxide. Well, we're going to use the same conditions here. Check it out. Now it's not the rich getting richer. It's the rich carbon, the one that has the hydrogen on it. That's the one that's going to take the hydroxyl. The other carbon that has no hydrogens on it, that's the one that takes the hydrogen. But look what we get again. We still get an enol, right? This is an enol. We have an alkene and we have an alcohol, an enol. However, this enol is not an acid, it's in base because you're in sodium hydroxide, and it is going to undergo a base catalyzed tautomerization, which is just a tsatsi word for an isomerization that involves the movement of a pi bond and a proton to give you not a methyl ketone, but an aldehyde. Aldehyde. So to summarize, we take a terminal alkyne, we do hydroboration oxidation. So I'll just put here hydroboration oxidation conditions. I'm not writing them down for a reason. And then we end up with an aldehyde. Now, if you're wondering, why didn't you just write the conditions that are shown right there? You could just read them right off the page. Well, I'll explain that in a couple of seconds. However, before we do that, I want you to look at the mechanism for based catalyzed tautomerization. And I'm going to put here, know this mechanism. Move that bus. Okay, know this mechanism. So we go here. What's the mechanism of base catalyzed tautomerization? The first step is a proton transfer, but now we remove a proton from the hydroxyl to make what's called an enolate. Hopefully you can imagine where that comes from. You've got the alkene, and then you've got an 8 because you've got a negative charge here. It's the conjugate base of an enol. It's an enolate. And in fact, we do a whole chapter. I think it's chapter 21 in organic chemistry too, where we spend a whole week talking about enolates, but that's neither here nor there. The enolate has 2 resonance structures, and this contributor ends up undergoing a proton transfer to produce the aldehyde. So you need to know this mechanism. I'll put it here again. Know this mechanism. Make sure you know this one. Very, very important. Now, something, again, that I avoided doing in the last slide was I said hydroboration oxidation, but I didn't write down the conditions. And there's a reason why I didn't do that, and I'll explain that to you right now. The reason why is if we use just the plain old the reason why is if we just use the plain old BH3 THF conditions, well, boron is actually a pretty small molecule. Okay, it's just BH3. Boron isn't big, and hydrogen certainly isn't big. So once you add one molecule of boron, now you've got a double bond, and it can add again, which is just going to give you problems. Okay, it's not going to give you the desired product. It gives you an undesired product. Therefore, how do we avoid it adding twice? What we do is we replace 2 of the hydrogens. We replace them with giant alkyl groups, so big that once you do the addition and you've got these giant groups on here, a second molecule can't come in and add again. What are these giant groups, you ask, or you might ask? Glad you asked. Well, one of them is what we call a cyamyl group. That's neither here nor there. You don't have to know the common name, but dicyamyl borane is one. And the one that my students like the most is 9-BBN. I've taught this class long enough to know that my students love 9-BBN. It's easy to remember. It's catchy, 9-BBN. We looked at bicyclic alkane nomenclature. So if you look at the longest bridge, 1, 2, 3, 4, 5, 6, 7, 8, 9, you can see why it's called 9-bora bicyclo. 3, 3, 1, nonane. Again, I'm not going to ask you the nomenclature of bicyclic boranes, but that's where the name comes from. And since you have got these giant bulky groups attached to the boron, you've only got one boron hydrogen bond. It prevents a second addition. You can only add once, and then the buck stops there. It can't add again. So we have to use the hindered borane. Now, let me just look at my notes here. I had something written, and that is for my students who are studying for the ACS final exam. ACS, besides using these bulky boranes, they sometimes will write something like this, where they'll put one boron hydrogen bond, and then they'll write something that looks like this. Okay, this is just a shorthand for saying that this is some kind of giant bulky group. Our textbook doesn't use that at all, so I'll scribble it down here, ACS, and maybe MCAT. I'm not sure. I'd have to look, or maybe you could look and tell me. But that is just another shorthand for a bulky borane. You've got something dangling or hanging off the boron. It's not a hydrogen. It's in the way, and it prevents the second addition. So there we go. So what happens is we have that modified borane. We convert the alkyne into the aldehyde. Again, it's not the rich getting richer. It's the opposite, right? For making, let me just draw the enol that's produced. You end up with the double bond, but now you've added the hydrogen to this carbon and the hydroxyl over here, right? To make this enol, which undergoes tautomerization in base. Okay, so we'll put here tautomerization in base to give you this aldehyde. All right, in dicyclyl borane, and you can put here or 9-BBN. That works. And I'll never use this, but you could put this to this kind of giant ring hanging off the borane. I'll never use this. Never. But it is found in the ACS study guide, and I know some students like those things. So there you go. Either one works. All right, hydroboration oxidation. And so to summarize, if we add water in a Markovnikov fashion on a terminal alkyne, we get a methyl ketone, right? CH3, so we get a methyl ketone. If we add it in an anti-Markovnikov fashion, we get an aldehyde. And that's it. And the conditions for Markovnikov addition are sulfuric acid, water, and mercuric sulfate. Anti-Markovnikov is a hindered borane. Again, instead of writing 9-BBN, you can also write R2BH, which this just means you've got two big R groups on there, okay? Or you could put dicyamyl borane. They all mean, or they all do the same thing, okay? All perfectly reasonable. And that's it, my friends. That's it. Okay, so make sure you know the enol that you would form here would be this enol, which undergoes tautomerization to give you the methyl ketone. And the enol that you would form here would be this enol, which undergoes tautomerization to give you the aldehyde. There you go. Not too bad. So let's take a look at a question. The first one, or both of them, just say identify the reagents. The first one, we're taking this terminal alkyne. Why is it terminal? Because it's got a hydrogen on one end, and we're making a methyl ketone. Could anybody tell me the conditions we would use for this? We want to make a methyl ketone. Methyl ketone. Yes, absolutely. My students are 100% correct. The conditions would be sulfuric acid, water, and mercuric sulfate, Hg. I'm kind of running out of space here, aren't I? Let's see, let's squeeze it down here. HgSO4. Great. Great, perfect. The next one, we're taking a terminal alkyne, and we're making an aldehyde. So this is an anti-Markovnikov addition of water across the triple bond. For step one, you could use 9-BBN. You could use R2BH. Here, I'll put or R2BH. So, or R2BH, or you could put dicyamyl boron, borane. Either one of those works. And then in step two, same as before in chapter 8, hydrogen peroxide and sodium hydroxide. And that is it, my friends. There you go. A couple of new sets of conditions to do the Markovnikov or anti-Markovnikov addition of water across a triple bond. Pretty cool stuff. Well, let's see here. We've got 1, 2, 3 new reactions to look at before we get into putting them all together and practicing some synthesis. I'm just going to go over this one kind of quickly. It's the halogenation of an alkyne. We talked about halogenation in detail in chapter 8 when we looked at the bromonium ion, and then the bromine comes in and attacks. So if you take an alkyne and you treat it with just a whole whack of a halogen, whether it's Cl2, okay, so you could use Cl2 or Br2, you're going to end up with a tetrahalide. Okay, just piles of, just everything that can add will add sort of thing, okay? And if you're wondering, why not iodine? If you try to do it with iodine, it's too slow. And then you can imagine with fluorine, it's the opposite. It's too fast to the point where it's violent and can cause an explosion. So we generally speaking frown on that kind of stuff. So a dihalide. Now, if you're wondering, well, instead of excess, what if you used exactly one equivalent? What would happen then? Instead of just adding too much, why don't you just add 1 mole for every 1 mole of your starting material? And the answer is you can do that. So if we have 1 equivalent of this, we can add 1 equivalent of the halogen, and that will give us a mixture of anti and syn addition to give us a mixture of the E and Z product. Now it says the mechanism for alkyne halogenation. It even tells you here in the slides, it's not fully understood. If it was the exact same as the mechanism for the halogenation of an alkene, all you would get would be the E product, right? Because the bromonium ion, you'd only get attacked from the opposite face, but we see that it isn't. It's clearly not, since you get a mixture. So this is an example of another mechanism you do not need to know. You can imagine if it's not that well understood, I'm not going to ask you about it, okay? So again, 1 equivalent just gives you a mixture of both the E and the Z dihalide. So that covers section 9.8. That was pretty fast. The next section is another section where there's no mechanism. And hopefully you remember that we looked at the ozonolysis of an alkene. I don't really have a lot of room here, but this is chapter 8. Just to refresh your memory, we took an alkene, we treated it with ozone, followed by DMS, and we ended up with, in that case, it would have been a pair of aldehydes. So you end up with this. All right, that's not a very good drawing, is it? But anyhow, that's ozonolysis, and we went over the skill builder for that, where you take the little eraser and everything. If you have an internal alkyne, so 2 R groups flanking the triple bond, what you end up with in that case is a pair of carboxylic acids. Now, there's no skill builder for this in the book, but it's kind of like, I need to zoom in here because there's not a lot of room. It's kind of like you have this like R1C, right? And then you have R2, D, like this, and then you kind of just put an oxygen here and then put an OH here, right? Like that. You end up with a pair of carboxylic acids is what you end up with. But if you have an internal alkyne, you break this, okay? So from the R group, you end up with a carboxylic acid, right? You put an oxygen here and then an OH here. But this portion here doesn't give you a carboxylic acid at all. It gives you CO2, okay? And you should know the Lewis structure for CO2, which is shown here. If I'm not sure if I stated this or not, I may have, I may not have. I can't keep track of what I'm saying maybe, but another fine point is that the second step in ozonolysis of an alkene is DMS, but with an alkyne, the second step is water. So just treat the intermediate with water, and there you go. And there is no mechanism. So no mechanism. I know there was a mechanism for the alkene one, even though I told you didn't need to know it, but there's no mechanism in our textbook that's even provided for this reaction. Let's see if we can do a couple of practice problems before we take a break. Let's see. Predict the products that you get from this reaction. So this is ozonolysis of an alkyne. What we're going to do is we're going to break this bond. It's an internal alkyne, so internal alkyne. We're not going to get any CO2. What we're going to do is we're going to redraw these pieces like this, and then we'll redraw this one. Then we have 1, 2, 3 bonds, 1, 2, 3 bonds like this. Then we put a little oxygen here, 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 and here. And that's the only thing we're going to get. You can clearly see that this molecule is identical, or both of these molecules are identical. Therefore, the only thing we get from this reaction is cyclopentane carboxylic acid, this molecule here. Is everybody, give me a thumbs up. Is everybody with me on that one? The ozonolysis of an alkyne, an internal alkyne. Okay, cool. The answer is on the next slide. I had it on there the whole time. So if you have an internal alkyne, you can see that it's a pretty cool reaction, because if you start with only 1 mole of this, you double. You end up with 2 moles. Yay! So you end up with way more material than you started out with. So that's kind of cool. It's a neat reaction. I've never found any synthetic utility for it in my life, but hey, it's all good. Let's try one more practice problem, then we'll take a little break here. Just draw the major products that are expected when this alkyne is treated with ozone followed by water. So we're going to take this cyclic alkyne. We're going to treat it with ozone followed by water. Now, let me just say something before we get in here. This molecule has a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 atoms in it. Because you're probably thinking, you know, Mr. Dean, how can you put a triple bond in a ring? I thought the molecular geometry here of an sp hybridized carbon was, you know, linear, so it has a bond angle of 180. How can you even stick that in a ring? If you look at the very beginning of this chapter, it tells you that even if you have cyclononine, a 9-membered ring with a triple bond in it, it actually decomposes. It's so unstable. So I imagine that what they're getting at is that you can only incorporate a triple bond into a ring once you have probably something in the order of 10 carbons or more. So I'm presuming that this compound might be, or is probably somewhat stable. You know, it's probably not the most stable thing out there, but it can be isolated. So this would be called cycloundecane is what you would call it. I don't ask you to name 11-membered rings, so let's not stress about that right now. But what are we going to do? We're going to cut this bond in half. And remember that when you have an internal alkyne like this, when you break it apart, you're going to end up with 2 carboxylic acids, right? You're going to end up with 1 here and 1 here. And so to draw the final product, which is a dicarboxylic acid, since they're tied together in the same ring, both of those carbons 1 and 2, let's just draw the carbon chain first. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 carbons. We're going to put a carboxylic acid at each end. And there you go, my friends. That's it. So this would be called undecane dioic acid. The name is not important, but give me a thumbs up if you're with me on that. Give me a thumbs down or ask me a question. If you're unsure about that one, don't hesitate to stop me. It doesn't bother me one bit. In case you never noticed, I like talking about chemistry. All right, there we go. Well, that brings us to the very last section of new reactions. And this is the alkylation of a terminal alkyne. So I'd like to take a short break before we take a look at this, because we're going to discover a way to make a carbon-carbon bond. Very important, so we need to take a little breather before.